So I went back to my undergraduate physics days, and I thought I'd just kind of, light is all around us, happening everywhere. We all take it for granted, but it's nice to just take some time, let's shine some light on light and go back to the fundamentals and the physics, the core physics behind it. So my goal, I have a big goal here tonight, is that everybody leaves knowing the colour of grass. Now some of you are smiling, but this is a serious task that I want everybody to leave with an understanding of that, okay? So I go to different schools, etc., and I posed this question and I met with blank faces. So and they think I'm slightly crazy when I talk about this, but I'm hopefully going to take you on a little journey, and then at the end you're going to come back to me with the answer. Firstly, can I throw it out there? What colour do we think grass is? If you're a physicist, don't answer. In case you probably do know. So what colour is grass?
Green. Blue.
Green. Blue. Okay, green and blue. Okay, we'll see. So without talking about colour, of course we have to rewind and ask this very big question. Well, what is light? So if I go to Google and I kind of take the best, maybe 2 or 3 searches, I get this kind of a sentence. Light is a visible type of wave composed of oscillating electric and magnetic fields propagating through space at a speed c. So quite technical, but for the physicists we're nodding, right? But for the general public, if you want to know what light is, that's probably not going to, illuminate your mind of, well, oh, that's what it is, eureka. So I thought I'd just kind of explore these kind of 3 areas within this sentence. Firstly, it's a visible type of wave. Secondly, it's an oscillating electric and a magnetic field, and it travels at a very unique speed, c. So working in reverse order, we'll start with c. So the speed of light, c, the very infamous speed of light. There's nothing faster in the universe. It travels at 300 million, well, 3 by 10 to the 8, so 300 million meters every second. So immense, right? We can't even imagine that. But way back in the 18th century, I think, or maybe it's about 1780 or so, Galileo thought he might measure this, and what he did was he had an attendant go about approximately a mile away, and each of them had a lantern with a shutter on it, and Galileo said, okay, I'm going to open my shutter, and as soon as you see the light, open your shutter as well, and we'll measure that time it takes. But of course, at the time, that distance was way too short to measure something that's travelling 300 million meters per second. So he proposed that it's either light is instantaneous, it's just there, it doesn't have a finite speed associated with it, or it's extremely, extremely fast. So it took until, again, about 30 or so years later, a Danish mathematician, and he was an astronomer as well, Ole Romwer, and what he did was he was looking at Jupiter's moons, and he realised that using Newtonian classical mechanics and crunching the numbers, that by looking at the moons, the orbit is approximately 11 minutes out, either 11 minutes sooner or 11 minutes later, depending on what side of the sun the Earth is. So he put that additional 11 minutes down to the fact that light has a speed. There's a finite number associated with it to actually travel. And he approximated that number to be about 2 by 10 to the 8 meters per second. So not too far off, so that was the best approximation at the time, until of course the Michelson interferometer refined that number to 3 by 10 to the 8, the number we all know. So that's the speed of light, that's our c taken care of. The next part, a little bit more challenging, and I must admit I needed to go back and refresh this in my undergraduate books. The fact that light is an oscillating electric and magnetic field. So let's just take the word field for a second, and if we think of electric fields, this is all electrostatic, so the charges are not moving. You've got 2 stationary charges and you've got this field surrounding them. And if you were to place an additional charged particle within that field, it would experience a force with going in a specific direction with a specific magnitude. So that's the vector taken care of, and the field, of course, are all these lines around it. Magnetic materials also have this magnetic field surrounding them as well, and like the electric field, if if a particle is introduced, it will experience this magnetic field. So that's it in an electrostatic form. But of course I've told you that it's electromagnetism, it's electromagnetic oscillating fields, so we need to combine them in some way. And building on the work of Oersted and Coulomb, which is all defining electrostatics, came Ampere. And what he noticed, when he discovered one day in the lab, that moving charges produce a new force. He never specified what it was, but it's not there when the charges are stationary. So this, after a bit of time, this law was refined and additional experiments were done, and the law was defined to a flowing electric current give rise to a magnetic field that circles the current. So you can see here, I hope, the diagram on the right. You've got your charge flowing through a conductor, and what happens is, as those charges are moving, you get a magnetic field that will curl around or circle around those moving electric charges. The magnetic field does not occur if the charges are not moving. So that was the first experimental evidence, and it's working towards bridging electric and magnetic fields. The next big person or discovery came from Faraday, which was that an electric field is produced by a changing magnetic field. So I brought a little prop with me in case you didn't believe me. And I'm willing to take any member of the audience to join me here, and I'm going to set something up. So I'm going to show you that if a magnetic field is changing, you'll get a current flowing in a current carrier. So who'd like to join me? Perhaps Aoibhinn, if nobody else.
Nobody else. Yeah.
Sorry.
Oops, the daisy. That's the best way to put this now. Maybe here.
Okay, so Aoibhinn, you'll confirm this for the people at the back. We have some currents carrying cable here, copper cable, just wound in a circle, connected to an ammeter. So that's going to read a current.
Show you that. So this is the ammeter. This is showing you if there's a current, it's currently reading 0. This is just a coil of copper wire, something similar. There's nothing happening, it's still 0. Okay.
Perfect. Okay, so Aoibhinn, this is quite a strong magnet, so don't go near anything metal because you'll suddenly be drawn to it. So what I suggest you do with this magnet is just place it inside that coil, right, and see do you get any reading on the ammeter.
I'm not moving, just placing it.
Just placing it inside the circle.
Right. Okay.
Do you get any reading of a flow of current?
Well, I did when I was moving it, but not when I put it down.
Okay, you're just taking the punchline. No, perfect. Okay, so the point is, Faraday's law is saying that if you just put a magnet beside a current carrying coil, you won't get anything, right? You verified that. There's nothing happening. But try it now and go in and out quite fast and see what happens to the ammeter.
So, magnet's in the coil, it's reading absolute 0, and now I'm just going to move it around, and the thing's just going like this. It's moving everywhere. So why is that happening, Arlene?
Thank you. So great. So the fact that the magnet is moving, the magnet, exactly,
it's
really strong. Leave it. I'll get it later. I was carrying it inside this foam ball, so that I wasn't going to be pulled along in the taxi. Like Aoibhinn demonstrated, that you'll only get this flow of current, of course, when the magnetic field is moving. So, those two key discoveries, as well as a couple of more, led to this theoretician Maxwell. Thank you. Bringing a big, strong person to come up and help us with this magnet. Maxwell kind of unified all of those independent experiments that were happening in these 4 very elegant equations. So these are known as Maxwell equations, and these define, okay, perhaps you're wondering where we're going. We asked how grass is green. Are you all still with me? I thought I'd stop on that point. Okay, nodding faces. Okay, good. So we're in the electromagnetic portion of the fact that light is an electromagnetic wave. So Maxwell's equations kind of bring together all of these aspects of electromagnetism, and I won't go into them now, we don't have time, and I can't remember, if I'm honest. But I could certainly give it a go, but I won't. But do check them out if you're not familiar with them. And what these equations actually allowed us, or Maxwell as a theoretician to do was describe how the electromagnetic, electric and magnetic fields propagate, interact, and how they are influenced by objects. So suddenly we have this unification of two fields of physics that were thought to be completely independent, and there was no experimental evidence for them at this point until later on. But this brings me back to the fact that light is an electromagnetic wave, and an electromagnetic wave is produced by an oscillating charged particle. So you can see Q here in the corner, that's my charged particle going up and down, and it stays stationary. But what happens is this oscillating charge causes a changing electric field, which will in turn give rise to a magnetic field. And you suddenly get this kind of perpetual maintenance of the charges stay stationary, but they're self kind of cycling and they move off. And that is light. That's what light is, these oscillating electromagnetic fields. And the first time I heard that, I thought my lecturer was drunk. But proves he wasn't at the time. At that particular time he wasn't. So, okay, so I thought I might show you what an electromagnetic field looks like as it's propagating. So you've got your magnetic field, which is the blue, and then you've got your electric field, which is the red, and they're propagating in a direction that's perpendicular to both the electro and the magnetic fields independently, both of which are orthogonal to one another. And what we note about these electromagnetic fields is that, they are self-propagating, so they're sustaining themselves, they're happening as a direct result of what we saw through a magnetic field producing an electric field, and then suddenly it's of course travelling at the speed of c. It's a transverse wave, so I made reference to that and the fact that they're orthogonal, and there's a fixed ratio of strengths between the electro and the magnetic fields. One thing to note is that, of course, most of you might know, light does not require a medium to travel through. So light, unlike sound, which requires atoms or particles in the air to vibrate and compress, to carry the energy, light does not need that. So it can, of course, travel in a vacuum. So depending on the frequency, so because light has a wave-like nature, we can characterize it in terms of its frequency and its wavelength. And of course, we all know that light carries energy. All we need to do is, put a magnifying glass onto something on the grass, and we get light from the sun, and suddenly you've got a burnt patch. So there is light. Energy is carried in the form of light. So exploring the fact that we've got a whole variety of frequencies to play with, if you categorize them, they're kind of represented quite neatly here in an electromagnetic spectrum. And you've got high frequency waves which have very, very high energy, and these are all a form of electromagnetic radiation, but the high energy ones are the gamma rays, and as you move across to these lower energy, low wavelength, or high wavelength, radio waves, we all exploit them in our everyday world. We have, for example, in gamma rays, we use them to treat cancer. In X-rays, they see through tissue, so you can get images of the bones. Ultraviolet, we get a nice tan from that. Infrared, we can thermal imaging, etc. inside a house. Microwave, we can cook our food, and radio we can use for communication. So we've been exploiting the electromagnetic radiation spectrum for many years. But I thought we'd just jump into the visible portion, because the rest is invisible, and it's only this very, very tiny portion in the middle that our eye is sensitive to. So point number 3, taking us back to the fact that light is an electromagnetic oscillating wave propagating. It's also travelling at the speed c, and it's a visible wave. So our eye is only sensitive between 380 nanometers up to about 750 nanometers. That's that visible portion inside the spectrum. And grass, which we might all think is nice bang smack there in the middle, about 520 or so. But this brings me to the point that I'm trying to get, which is, what is colour? So colour is it's actually not a physical property of any object. Light is only something we see because it's been reflected off the object, and our eye, either some energy has been absorbed and we get the reflected part it doesn't like, the eye collects this and tells the brain the colour is a certain colour. So that's, I'm kind of giving a hint there. So it's not a physical property. So colours are the way our brain, by use of our eyes, interprets this electromagnetic radiation of a given wavelength within the visible spectrum. So in the case of grass, so for some reason during the process of photosynthesis, where the grass, the chlorophyll in the grass takes the light, it uses it to form food. It particularly likes the blue and violet portion, that particular energy range. And it particularly likes the middle one? Oh yeah, sorry. So it particularly likes the blue and violet, this particular energy, and it absorbs this energy really, really well, orange and red. And the part it doesn't like is in fact green. So I ask you again, what colour is grass? By definition, if we say grass colour is a property that of the reflected light, okay, we'll all agree it's green. However, if you look at grass from perhaps a physicist's point of view, you would say that it's red, orange, yellow, blue, indigo and violet, and not green, because in fact that's the colour it doesn't like. It doesn't want to be green, it doesn't absorb that energy. So it's the reflected portion that you pick up with your eye. So, what colour is grass? Yay!
Not green.
Excellent, not green, excellent. So, as a physicist, light has always been to me the most interesting thing, and I could have taken this in a whole array of directions. This is the way I went with it tonight.